Good morning to everybody. Uh, this is the second lecture in the online series of digital communication. In the first lecture, we have learned about the necessity of digital modulation scheme. So we have discussed over there the baseband signal is binary in form, which is of low frequency signal, and if we are transmitting directly that signal without the modulation, then at the receiver side we need a larger antenna to receive the signal, and in some cases the size of receiver antenna is in kilometer that we cannot afford. So it is essential that this low frequency baseband signal can be converted to high frequency signal, and this process is known as a modulation. So modulation is very essential process if we are dealing with a wireless communication. This is not required if your transmission use the wire line channel where everything is transmitted by the wire and antenna doesn't require. Now with the continue of our previous discussion, today we mainly discuss about the various digital modulation scheme. Even we discuss about the important modulation scheme ASK in a detail. So here the various digital modulation scheme has been displayed. We can start with ASK. It's known as a amplitude shift key. It can be further classified as a binary amplitude shift key and MRE amplitude shift key. Then the another category is known as a FSK. It's known as a frequency shifting key. It can be further classified as a binary FSK or MRE FSK. The third important digital modulation scheme is known as a phase shift key, which can even further classify as a binary phase shifting key or MRE phase shifting key. Then we even look around the quadrature amplitude modulation scheme with the different variations of QM like as 4 QM, 16 QM, 256 QM and so. The another important digital modulation scheme that we will learn is known as a continuous phase shifting key, and we even learn with the various entities of minimum shift key and Gaussian minimum shift key. This Gaussian minimum shift key is very important modulation scheme, and it is widely used in third generation GSM system. So whenever you will learn the wireless communication system and about the third generation wireless communication system, so you will find the GMSK is the key modulation scheme over there. We will learn about the various important parameters during the discussion of each and every modulation scheme. They are the power consumption, how much power is consumed of various modulation scheme. Then we will see about the bandwidth requirement. The bit error rate performance is also very important parameter, and the scheme which has a lower bit error rate is considered as a good scheme. Then we even learn about the spectral efficiency of various modulation schemes. So these are the 4 parameters. Each and every modulation scheme can be justified according to this parameters. Now we go in a detail of the amplitude shift key. It's simply known as the ASK. A stands for amplitude, A stands for shift, and K stands for key. This ASK digital modulation scheme is very similar to the amplitude modulation schemes that we have already learned in the last semester in the analog communication. So here we see the difference about amplitude modulation and ASK scheme. So if we start with the analog communication, so this is the amplitude modulator. It has a two input, x of t. This is known as a baseband signal. This signal is of lower frequency signal and analog in nature. Then it is modulated with this carrier signal, which is of high frequency signal, and it is also analog in nature. So this both the signal x of t and c of t is modulated in this amplitude modulator, and finally the output signal is produced as a y am of t. This signal is also analog in nature. So in analog communication, the input x of t is analog in nature. The output which is produced at the modulator, this is also analog in nature. And the envelope of this y am of t, this is directly proportional with the applied input signal x of t at the amplitude modulator. Now, if you see the digital communication, and the special case in digital communication is ASK. So this is the ASK modulator, which has also two input. One input is x of t, but here it is in form of a binary data, which we can say is a digital. Now then it is modulated with the carrier signal, which is of high frequency signal. This x of t is a lower frequency signal, and then finally we are producing y-ask of t, and the waveform will be look like this. This is analog in a form. So we can observe here the input of ASK modulator is digital, but the output of ASK modulator is analog in a form. So this is the basic difference between analog communication and digital communication. Both have an analog output, but the input is different. In analog communication, the input x of t is analog signal, where in digital communication, the input x of t is a digital signal. So here we can see the difference. In amplitude modulation, the input signal is analog in nature. The output signal is also analog in nature. Where in ASK, the input signal is digital in nature, which is in form of a binary, and output signal is analog in nature. So this is a mistake. We can make it correct. This is analog in nature. So here we can observe the very important concept here is in amplitude modulation, the output of y of t signal depends on the amplitude of input signal, and the envelope of y am of t is directly proportional with the shape of your input signal x of t. So that's why it is known as amplitude modulation. The amplitude of your carrier signal is changed in accordance with the applied input x of t. The same happens here in digital communication also. In digital communication, in ASK modulator, the applied input is x of t, and according to the shape of x of t, here you are getting the carrier or you are not getting the carrier. If the input signal x of t is a 1, then you have a carrier. If there is a 0, you don't have a carrier. Then if there is a 1, you have a carrier. So this both have a similarity in this sense. The output is largely depends on the amplitude of input signal. But the difference between these two is in analog communication or in amplitude modulation scheme, the input and output both are analog in nature, where in digital communication your output is analog but the input is digital in nature. So this is what have been written over here. Now we will see the mathematical expression of amplitude shifting key. So any amplitude shifting key signal in a time domain can be represented as a square root 2 EB by TB into cos omega CT when the applied input x of t would be a 1. X of t is already a digital signal, so they may have a two possibility, either it may be 1 or 0. So if the binary 1 is given as an input of amplitude modulation, then the output produced is square root 2 EB by TB into cos omega CT. And if the input bit stream is a 0, then produced output would be a 0. Now in this equation, EB is the energy per bit. So if your 1 can be represented by some pulse, so whatever the energy is consumed by those pulse, like this is a pulse, and whatever the energy is consumed by this pulse, so this is known as a EB. So EB defines the energy of a pulse, and TB defines the time duration of pulse. So if your pulse is of some duration TB, so that can be defined here. So here this is the amplitude A can be represented in form of a power that later on we will discuss in a detail about this equation. So here the amplitude can be represented as a square root 2 EB by TB. Now how this expression comes, we go in a detail about this. So let's say any amplitude shifting key signal can be represented by cosine waveform. So if the input bit is 1, then the output would be a simply cosine signal, and this cosine signal can be represented with the frequency of omega c and the amplitude of A. So simply represented by A cos omega ct if the input bit is 1. Right, so here we are assuming the x of t is 1, because if x of t is 0, then the output is also 0. So this is the special case when the applied input is 1, and then we are transmitting the cosine signal with some amplitude A and the frequency omega c. Now if we find the power of the signal, so we have an equation to find the power can be simply defined as the 0 to t, and whatever the signal here is y Ask of t. We take the square, absolute value square, and with respect to t. So that way you can find the power. If we find the power in this way, we can find this is a cosine waveform, so power can be found as a square by 2. So power here is directly proportional with the amplitude square divided by 2. But the power can also be represented as energy per second. So that is the energy for some duration of signal divided by the time period of the signal. So here we have already discussed, if there is a pulse which represents a 1, and if the energy of this pulse is EB and the time duration of this pulse is TB, then the ratio of EB by TB will give us the value of power. But the power also can be represented as a square by 2 as per this formula. So then if we correlate this both the things, EB by TB and a square by 2, and found the equation in a form of a, then A can be identified as square root of 2 EB by TB. So the same value of A, if we put here, if we follow this path and if we put the value here, so the equation becomes a square root 2 EB by TB cos omega ct, and the same equation here is represented to describe the amplitude shifting key when the input 1 is transmitted. Okay, so that is the similar things which has been described over here. The carrier signal is transmitted if the input binary signal is 1. So if the input x of t is 1, the output of a modulator is simple carrier signal with this amplitude square root of 2 EB by TB, and the multiply with the cos omega ct, right? So here there would be one more terms you can consider here is multiply with the cos omega ct, right? And if the x of t would be a 0, so no any signal is transmitted, no any carrier signal is transmitted, and the output of modulator Ysk of t would be a 0. So these two things you have to understand here. When the input bit is 1, the output is square root of 2EB by TB into cos omega Ct, and when the input bit is 0, so output is 0. Now here there is a graphical representation of Ask signal. Here the bit are changing at the boundary of a clock, and consider the every bit is changing at a negative edge clock of the clock signal. So this is the negative edge transition of a clock from 1 to 0, and at this negative edge the bit is changing. So the bit 1 is changing to the next one at this boundary, and this is also changing from 1 to 0 at this boundary, and so for all. So for every negative edge the bit is going to change. So this duration of this clock is simply considered as a TB time period or bit duration. Now assume your input signal x of t, which is applied here, is a binary sequence. So one binary sequence has been considered here, that is 1 1 0 1 0 0 1. And assume the case of any on-off kind of a signal, input x of t is the on-off signal. So 1 can be represented by positive pulse and 0 can be represented with a no pulse. Then again 1 represented with the positive pulse, 0 with no pulse, and the same for all other sequence also. So as per this equation, if the input bit would be a 1, we are transmitting the output as a square root 2EB by TB into cos omega Ct. So that is a multiplication sign here, and if the input is 0, so output would be a 0. So as per this is the input of modulator and this one is the output of modulator. So if the input bit is 1, so we transmit the cosine signal here, that can be shown here. This is the portion. If the next input bit is also a 1, so again we transmit with the square root 2EB by TB cos omega Ct. If the input bit is 0, then we are not transmitting anything here. Then again 1, we are transmitting the cosine signal, and same for all other bit also, right? So Ask is also sometimes known as a on-off key signal, because input is x of t, the on-off signal, and as per this on-off signal we are transmitting the signal with either with the amplitude of square root 2 EB by TB cos omega Ct, or we are not transmitting anything if the input bit would be a 0. So this is the case that has been described over here. Now the another very important portions that we are going to cover is about the constellation diagram. So constellation diagram is just a represent the phase. This represent the phase and amplitude of symbol. Right. So this graph will this graph is simply known as a constellation diagram. This graph has an imaginary axis which is represented on a y-axis. So y-axis is your imaginary axis. There is another axis. This axis is known as a real axis. So real axis it just represent the amplitude of a signal which has no phase or zero phase. Right? So they have only real value, no any imaginary value. And if your signal has imaginary value and real value both, so it can be represented on a y-axis. So here this you have to understand. So this is your y-axis, which is imaginary axis. This is real axis. Now here, what is the symbol? We have to understand this thing. So basically there are two symbols. This is your symbol 1, right? And this is your, you can say, symbol 2. So what is this? This is your symbol 1, symbol 1. And this is your symbol 2. So symbol 1 is nothing else but it is simply represented with only the amplitude. So here the symbol 1 is simply square root of 2 EB by TB. And this is a real part. It doesn't have any phase inclined with this. No, it's not a complex value, nothing. It's simply a real part. And the other symbol can be represented by 0. So now, what is the symbol duration here? So if we see the symbol duration, so symbol duration is the TB. The same symbol repeat after TB time interval. So symbol duration is same. So here we can say the this constellation diagram, it just represent the amplitude and phase of a different symbols, and the symbol here is equivalent to bit. But this is a special case of ASK. So for ASK only, this is possible. The every symbol is roughly considered as a bit, right? Because if we find here the symbol is if you find here the symbol 1 and 2, so symbol 1 is square root of 2 EB by TB, and the symbol 2 is simply defined by 0. And when the symbol 1 is available at the output, when the input is 1, and whenever the symbol 2 is available at the output, when 0 is the input of modulator. And what is the phase here? So square root 2 EB by TB is a real part, so there is no any phase is inclined, so phase is 0. The same for second one, the amplitude is 0 and the phase is inclined phase is also 0. So here there are two symbols are there. The symbol 1 is the square root 2 EB by TB, and the second symbol is a 0. So in this constellation diagram, if we put one dot here, so 0 is put at the origin, and the value of square root 2 EB by TB is a real part, so it can be put in a real axis, and on this real axis we put it over here because it's a positive and real. If something is negative and real, we can put here. If something is imaginary, pure imaginary, then we can put up here and positive. And if something is imaginary and negative, we can put something over here. If something is complex conjugate with some real part and imaginary part, so we can put here, 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 and here, depends on the phase angle. So this shows the constellation diagram, which simply represent the value of a symbol with its amplitude and phase. So it's a representation of the symbol with including its amplitude and phase. Now here, one assumption in ASK is the symbol rate and bit rate as same. So symbol rate is the number of symbols we are transmitting in a 1 second, and bit rate is the number of bits we are transmitting in a 1 second. In ASK, there is no difference between symbol and bit, because if there is a 1 bit, we are transmitting square root 2 EB by TB, and if there would be a 0, we are transmitting a 0. So the thing here, the duration of the symbol, if we say this is the duration of our symbol, right? So it is simple, the duration of our bit. So both have the same duration. Thus TB is the duration to transmit a 1 bit, and TS is the duration to transmit a 1 symbol. Both are same. So the number of bits or the number of symbols are transmitted in a particular duration are same. So in that case, they are approximately, the symbol and bits are same, then the symbol rate and bit rate is also same. But this is not a case for all other schemes. Whenever we discuss about the QPSK, quadrature, amplitude, modulation, shifting key and all, so we'll identify there is a difference between symbol rate and bit rate. Now we came to the bandwidth of ASK signal. So if you have to find the bandwidth of ASK signal, so we have to go to the we have to find first the power spectral density, and to find the power spectral density, we have a signal y ASK of t in time domain. We take the Fourier transform of this, and we take the absolute value square of this frequency domain version, and finally we find SY of the power spectral density of amplitude shifting key. And if we plot this power spectral density with respect to the frequency, so this graph can be obtained. So in this graph we can see this is the region where all the frequency component lies. So it's known as a bandwidth of your signal. Now in ASK signal we have only single carrier signal is there. Therefore its power spectral density is also concentrated with the single carrier fc, that is the cos omega ct, and 1 is represented as square root 2 eb by tb cos omega ct. So and 0 is represented with 0. So if we take the power spectral density here, so that is concentrated to the frequency, carrier signal frequency fc, and the bandwidth is small over here, that is simple rb, or maybe the minimum you can define as a b. Now here we will see how the Asc transmitter it can be constructed. So in amplitude shifting key, your Yask of t is simple multiplication of the two signal. It is x of t and another carrier signal which can be represented as square root 2 eb into tb cos omega ct. So here we can say if here if we are applying 1 at the input, so at this point we have a carrier signal, right? It's simply known as a square root 2 eb by tb cos omega ct, and if the next bit would be a 0, so there would be a 0. Again if there would be a 1, so there is again one carrier signal with square root of 2 eb by tb cos omega ct. So this one is square root of 2 eb by tb, right, multiply with the cos x is omega ct here, and this is simple 0. So Yask of t is simple the multiplication of x of t and this term square root 2 eb by tb into cos omega ct. So the transmitter is very simple. It simply have a multiplier or maybe double sideband suppressed carrier which also work as a multiplier, and then finally produce output is the multiplication of the two input signal. Now if we go to the receiver side, so we may have a two possibility. Most of the receivers can be classified basically in a two category: coherent receiver or maybe a non-coherent receiver. The coherent receiver is a receiver in which in the time of a demodulation it used the same carrier signal which has been used at the transmitter for the modulation. So modulation is done by using some carrier, and demodulation is also to be done by using the same carrier. Then we have a coherent receiver, right? But sometimes the information like as a carrier is not available at the receiver, or there may be a possibility if you are transmitting your signal because of Doppler shift, your transmitting signal frequency is going to change, and whatever the carrier at the receiver has not the same frequency as what has been received. So you are receiving, you are transmitting fc, but because of Doppler shift you are receiving as fc plus delta f, and receiver has a carrier signal with fc frequency, so they both will not match, and in this case we have to use the non-coherent receiver. A non-coherent receiver is a receiver which detect the original signal from modulated version of the signal without using the carrier signal. So this is the non-coherent receiver. Now if we start with the coherent receiver, then the coherent receiver here Yask of t signal is received, right? So the signal which is received over here is like in this form. It is multiplied with 2 cos omega ct. The 2 is used basically to normalize the value of 2 which is produced later on in mathematical expression, and this is simply work as a multiplier. So this multiplier and this multiplier are roughly same. So transmitter and receiver use the same multiplier here. So whatever the signal is received here, it is simply multiplied with 2 cos omega ct, and the output produced at the multiplier is y dash Ask of t signal. This is passed through the low pass filter to get the original signal r of t. So this r of t is roughly approximate the x of t signal, the signal or before modulation or the baseband signal. So this signal is simply decoded here. Let's say this carrier signal is removed and we have a positive pulse, then this one is decoded as a 0, and then we can decode the 1, right? So similar way we can decode the signal. So we see the mathematical expression how this can be achieved from this point, let's say the point of x1, and let's say this point here where we are getting the original signal back, it's a y1. So how this travel journey from x1 to y1 can be achieved, right? So we will see about this. So let's assume the signal which is received at the input of receiver antenna is Yask of t, right? And it is multiplied with the 2 cos omega ct. So I need to replace this. It's a simple multiply with the 2 cos omega ct, right? So this signal Yask of t is this one, and this 2 cos omega ct where it is multiplied. So it is multiplied here, and this operation is performed by this multiplier. So now I represent Yask of t in its original form. Let's assume here this is for bit 1, x of t is 1, because if x of t is 0, so everything would be 0. So if x of t would be 1, so we have this portion, this is the portion, and this portion is simply square root of 2 eb by tb cos omega ct. It is multiplied here with 2 cos omega ct. We go with some mathematical expression and then simplify this. So that is the cos square omega ct, cos and cos square omega ct can be simplified as a 1 plus cos 2 omega ct by 2, and this is 2 will be cancel it out, and this is not there, sorry. So this is 2 and 2, this will be cancelled out. So finally we have the square root of 2 eb by tb. It's a 1 plus cos 2 omega ct. If you multiply each term with square root 2 eb by tb here, so the first term is square root 2 eb by tb plus square root 2 eb by tb cos omega ct. Now this is a representation of 1. If this is received at the receiver, it will be decoded as a 1. But this term, the second term, is a extra term. So this one is desired signal, we can see, and this one is the extra term. And this y dash ask of t is the signal which is available at this point. At this point. Now this one is consist the two terms. One is the desired one, and the second one is the extra term. So here we need some circuit which block this second one, extra term, and allow to pass only the desired signal, right? And this one for better analysis, if we take the Fourier transform of this and draw the power spectral density of y dash sk of t signal, then we can find this cos 2 omega ct is located somewhere here at the frequency of 2fc, and the another term is a pure DC term, there is no carrier part, so it is located at the 0 point here. So at this 0, this term is you can say the square root of 2 eb by tb, right? So this one is located. So this one is the desired term here as per that one. This is the desired term. This is representation in a time domain, and this is the representation in a frequency domain. This is the frequency domain representation, and this is the time domain representation. So this portion is the undesired term, or maybe extra term. We need to remove this. So what we can do here, we can apply some filter here, and this filter is h have a response of h of omega. We can convolute in time domain and multiply in frequency domain. And this filter is simply known as a low pass filter, which allow to pass only the first term and block this one, the second term. So low pass filter is allow to pass the first term and block this one. So then this low pass filter is designed accordingly. So at the input of low pass filter we have two terms. One term is square root 2 EB by TB, which represent a 1, and the second term is this one, square root 2 EB by TB into cos 2 omega ct, which is undesired term. By passing through the low pass filter we block the second one and allow to pass the first one. So here at the output R of t we have only the signal which is available is simple square root of 2 EB by TB, and this will can be encoded as a 1, right? So the same thing is it can be represented here. But if your amplitude shifting key have a 0 bit or may have a 0, then in here we can follow the same procedure which has been discussed here, mathematical equation. So everything would be a 0, and finally your receive signal R of t, or maybe recover signal you can say, because receive signal is the input of your antenna, and this is R of t here we are obtained after doing some processing. So this is better to say recover signal. So recover signal would be a 0, because if input would be a 0, so if you follow this procedure everything would be a 0, and finally we are getting the 0 as an output, and it can be detected as a 0. Okay, so this is a coherent receiver. So here what we can observe is whatever the input signal we have used here, this is a transmitter, so we have used one carrier signal here as a cos omega ct, and in the receiver we are using the same carrier signal. Yeah, definitely it is up with a different amplitude, but the shape and frequency of a carrier signal at the receiver side is identical to the shape and frequency what we are using at transmitter side, right? So receiver is using the same carrier signal for a demodulation what the transmitter has used for a modulation. So this is known as a coherent receiver, right? Now we go to the next portion about the non-coherent receiver. So in a non-coherent receiver we don't have a carrier at the receiver to decode the signal, so we will follow the procedure of a rectifier. Let's say apply here y Ask of t signal, right? I can remove from here, right? So this is apply here, that can be passed through the diode. So what happens here, the input which is apply here is the signal like this. After passing through the diode will clip the negative value, so we have only this value, then like this, and this signal have two component, desired component, undesired component. Then passing through the low pass filter we can get the R of t signal here, and this R of t signal is similar to the input signal. So one can observe here we have not used the carrier signal anywhere. Whatever the input we just pass through the clamping circuit by the diode, then the clamping circuit or diode is simply replace the negative portion, then the signal have both the parts, desired and undesired, pass through the low pass filter, and we get the desired outcome here. There is another, so this is the first non-coherent envelope here. The same thing can be achieved using a capacitor, and so we may have an envelope detector. So input is apply, pass through the envelope, and after passing through the envelope we are getting here our desired signal, recover signal R of t, and this is roughly similar to the X of t, right? So this is all about the amplitude shifting key, and in the next lecture we'll discuss about the MRE. We'll discuss about the MRE ASK in the next lecture. But here, before we conclude this lecture, we have to go through some merits and demerits of ASK. So the merits you can identify over here is simple to design, because the transmitter has only one multiplier need to deploy, and this multiplier will serve its goal. The two signals are given as input, and then we are producing the output. So design is very simple in this case. The bandwidth requirement we have observed here, and in this bandwidth requirement we observe there is only single carrier is there, right? So all the power spectral density is concentrated nearer to this single carrier, so they don't require a larger bandwidth. So bandwidth is also small, and which has also the advantage here. The spectral efficiency is the number of bits we are transmitting in a one time duration. So here in a one time duration, 1 bit duration, right, we are transmitting only one symbol, and that is considered as a poor, because later on we will discuss about the various modulation scheme where in a 1 bit duration we are transmitting a multiple symbol, or maybe a one symbol may represent the multiple bits. So that part we will address at later stage. But with compared to that part, here we are transmitting only one symbol within a 1 bit duration, so that can be considered as a lower spectral efficiency or poor spectral efficiency, due to the reason of same symbol rate and bit rate. And yeah, power consumption is here higher, right? The reason is we are using a cos omega ct, and to achieve the same bit error capacity we need to make it power double. So this is not a power efficient scheme. Later on we discuss about various modulation scheme which is more power efficient than ASK. So here it is enough for today, and in the next lecture we discuss about M, REASK, and then FSK and all other modulation scheme. Okay, so thank you all.